So this is our second part of class 2, where I want to relate, some randomness and noise to the acoustic domain or the signal domain, and a little bit introduce the concept of music information dynamics on, just as an idea with some mathematical formulation, but the math of music information dynamics and the concepts of randomness or quantifying randomness like entropy is really important in machine learning, but we will kind of just mention here, we will not cover the details. So kind of bear with me, with the fact that, some things will not be really mathematically fully defined. Okay, just a sec. Okay, yeah, I think we're okay. So just the idea of noise, right? We spoke about musical structures. We said that this is a very limited set of acoustic phenomena, the notes, and how we organize them in scales, and how we put them together simultaneously in chords. And rhythms are also very specific ways of organizing them in time. So the concept of noise many times also kind of conceptually was contrasted with the sound structure. The intuitive notion of noise is something unpleasant, right? You have these noises of machines, or it might be even music, but when it's totally out of context, it becomes noise. So it's frankly just another sensation of sounds, right? It's not that noise is totally different experience. It's just that it's a sound or acoustic phenomena that is not appropriate in some sense. But trying to be a little bit more specific, when we spoke about structured sounds, like the pure tones, we could say, well, a sine wave, it has one frequency, well-defined frequency, and really, I mean, this is just, you could say this is that's how we define a frequency. You might have other ways of representing time patterns. Fourier transform really makes this mapping of a sine wave, a very specific pure shape of a waveform, to a single number. If we have periodic sounds which are more complex, we spoke about the idea that it might have multiple frequencies, and because this is periodic, you will have frequencies which are these harmonics. So they're partials or overtones, but for a periodic sound, they will be spaced at equal intervals, and these will be the harmonics and multiples of the fundamental. So this is kind of just a quick reminder of the acoustics that we studied so far. Now, noise, if we run noise through FFT or frequency analysis, or if you a lot of these experiments actually are fun to do with if you download software like Audacity. I put the link in the first set of slides, which is just a sound editor. It has a spectral analysis thing, so you don't need to program anything. You just kind of take a sound file, you throw it in, or you press on the record button and you record some noise. When you look at the spectrum of noise, you will not see these nice lines. You would see most often kind of very jaggy, kind of like continuous shape. So in some mathematical definition, actually, they define noise as something that has a continuous spectrum versus deterministic sounds or sequences or time series that are not totally stochastic. They would have spectral lines. So not only that, kind of intuitively we find, or empirically we find out that continuous spectrum tends to be perceived as noise. It actually trickled down all the way to some mathematical representations of what is randomness and what is something that could be predicted, has structure, stochastic versus deterministic. But staying on this kind of more of an intuitive and acoustic level, noise would be something that doesn't have a sensation of discrete tones. It might have a lot of frequencies, infinite, not so much in the sense of infinite number of frequencies, because we will stop hearing these frequencies at a certain point, but infinite in the sense that they're continuous. I might have a whole band of frequencies here rather than a spectral line. Many times we kind of think about these as bands because also we hear our perception of sound usually works in frequency bands. So we can still apply these band limited filters and get a sense of whether across the filters these things have a lot of energies, or do we look for a spectral peak. But often we kind of consider this in terms of logarithmic or octave band representation. Now, do we have any kind of mathematical measures of noise versus periodicity? So a very intuitive measure, okay, is something called spectral flatness. Spectral flatness actually is also recognized as one of the music information retrieval features. So a lot of libraries, like Librosa, have a bunch of ways of taking a spectrum and summarizing this into a number. One typical different measure would be spectral centroid, like where is the most kind of, where is the centroid from? If you think about the distribution of energies over different frequencies as sort of like a probability, if you want, or weights, right? So you can measure the centroid, and this would be one way of characterizing a complicated spectral shape by one number, and that's kind of where most of the energy, or maybe not where most of where the energy on the left and right, where it's kind of the balancing point. If you think about the spectrum as some kind of a spread of mass or spectral energy across bands. So spectral centroid is just one idea. You can think about spread. So spectral flatness measure, going back to the slide, is a different measure, and it's just a function that, I mean, that's what the name is, what it implies, that's what it tries to do, is to consider how flat a spectrum is. Now, why we care about flatness? Well, first of all, it's clear that if we have spectral lines, they're not flat. Now, we said that noise is usually continuous. We didn't necessarily want it to be flat. But if a noise is flat, which means if this graph is a straight line, we would usually call it white noise. Why do we call it white noise? Just because the idea that if you think about frequencies in analogy to color, if you take a color wheel and you spin it with all the colors on it, and when they mix together, you actually have a sensation of white. So we kind of borrow this term for sound as well, and we say when we have all these frequencies and they mix equally, we call it white noise. I mean, it has no whiteness in it in terms of perception, but this is kind of the ideal noise that has equal energies in all frequencies. So if we want to measure now something, whether it's flat or it's spiky, we can use this very simple formula. I think this is the easiest way to think about this. So just think about S and omega here are frequencies. Okay, we sometimes use F, we sometimes use K, sometimes we use omega. It's really just a way of convention. What we're trying to do, we will use discrete index if we know what a Fourier index is. We can use F if we know how to translate this to Hertz. And we might use this as omega if we want to use this as angular frequency. Basically, it's 2 pi F. So just, it helps to get used to all these terminologies. But again, you can put index I here if you wish directly. So this is a vector, or if you want to think about this as a function, if this was continuous, that has some kind of a shape, right? So you can kind of draw the values of S as the index I grows up from 0 to n or 1 to n. So if we want to measure how flat this function is, which means are all the SI's equal, you have here basically an expression of a geometric mean, and this is the usual arithmetic mean, right? So this is just taking the average, and this is taking the power and then taking an nth root of all the products. So no power. This is a product, and nth root of the product, and this is sum divided by n. I kind of urge you to just check out this formula. I mean, it has nothing really specifically to do with signal processing or statistics. It's just like a hack. You can think about this. This number, okay, will give you 1 if all the s's are equal. So just as a quick thought experiment, if all the s's are 1, okay, so you'll have or some value, let's say a, okay? So if all s is equal a, you have a to the power of n, and then you take the nth roots, you get a here, right? And if all the s's are a here also, so you have n a's divided by n, you have a divided by a, and you get 1. So if all the s's are equal to the same value, the spectral flatness is 1. And then you can see that if you have a situation where you have just 1 peak and the rest are 0, the spectral flatness will tend to go to 0. So it's kind of a function that looks into the spectral flatness of a sequence of numbers, or spectral flatness. It's just a function that looks if a sequence of numbers are all pretty much the same, or they start wiggling or jumping around. Now, this is just a way to rewrite the numerator as an exponent with a log here. But I would like you to notice this kind of an interesting notion. Here is the sum of the log of s, and here is the sum of s. So here we're averaging on the log. And now let's go back to the spectrum. And we see that we have something interesting here. We have, of course, it's exponentiated, but here it's an exponent of a mean of a log spectrum divided by the mean of the spectrum. This is kind of a good point just to introduce the concept of information rate, which is something I find very useful because it can suddenly makes the connection between just a function that measures flatness of a sequence of numbers to more of an information theory concepts that we will start talking about next week. But for the purpose of just relating these two without going through information theory, information rate is just a log of the spectral flatness, okay? So let me kind of try to show, and I hope I do have the example here. And let me see if when I'm sharing, I share the audio, yes, okay. So here's the sound, okay? And what I'm showing here is this information rate, which is basically a log of spectral flatness. So just to notice, because we use now a log with some scaling and a minus, we said the spectral flatness will be 1, okay, for flat signals. Well, and 0 for the other way around. So because we go through the log, it becomes the opposite. If spectral flatness is 1, this information rate of the row is 0. Okay, so row here 0 will indicate little structure. And on the other hand, if this becomes a small number, the spectral flatness, the log of this becomes a big negative number. With the negative, it becomes a positive number. So what I'm trying to explain is how to look at the black graph. The black graph is analysis of this log of the spectral flatness, or something that I will call later and explain why I call the information rate. And what it tries to show is that when you have high peaks, the signal should have a lot of structure, and when it has when it drops down, the signal should have less structure. Okay, so let's a little bit observe the spectrogram, and then I'll play it, and it will make much more sense. And we said that when we see these lines, okay, these suggest that there is something like a pitch going on, right? So you can see whenever we have lines, and here we have even 2 lines, this equation, basically by doing the spectral analysis and calculating spectral flatness, taking the log, can show you that there is structure here. For some reason here, the structure a little bit drops. Here it becomes much more substantial. Now, in areas when we have these blocks of energy, which are not lines, but they're like continuous, and this is where the idea of noise comes in. This is most likely noise, because it has a lot of frequencies which are very close to each other. They're not spectral lines. They are kind of noisy. So reminding you how to look at the spectrogram, each column here is a slice through one of the FFTs. And the color coding is basically how strong the energy is. These are the frequencies at this window in time. So you can see that at every window here, you have sort of like a continuous range of energies, or the continuous frequencies with high energies. Then the energies drop, and here you have maybe again a little bit more of an energy, and so is here. So you can see that whenever you have a continuous spectrum, you get a lower or less of a structure in this information rate function. And here it's also noise, so you can kind of have also, like, even though the band of frequency is different, so it doesn't really tell you where the band of frequency is, but the fact that there is a continuous frequency band, it gives you a lower number, finds the structure. Again, a lot of continuous frequencies, drops down. Here there's practically very little structure, so it even goes lower, and so on. Okay, so what I suggest, let's listen to this sound. I'll try to follow with the cursor to the best of my ability, but just remember that whenever you hear a tone, you're probably here. Whenever you hear some kind of a band of noise, and you can give away, or a spoiler, this is jungle noise. So some of them are like bird calls and chirps. So whenever you have like a noise, you're in one of these areas. So let's hope you can hear this. So, I think it's kind of pretty evident, pretty convincing that, this function can distinguish between, these kind of woo, whatever the pitched calls, versus these chirps that were bursts of energy in much higher frequencies, but also continuous. So, I mean, are they pure noise? They're not pure noise, of course. And I'm sure that the animals have ways to interpret this much more than we do. But I mean, this notion that you can kind of have a function that considers how structured the sound is, I think, one basic idea that at least corresponds to the intuitive notion that we categorize noise differently from sound. Without going to justify any of these concepts, I just want to throw in a concept of entropy. And we did not define entropy here. We'll define entropy later on. Those who have seen entropy as P log P, or whatever in discrete or continuous way, entropy is a central notion of trying to quantify how much randomness there is in a random process. Because even if you have a random process, it might have different amounts of randomness in it, or complexity, or uncertainty. So you can think about entropy as uncertainty in your outcome of generating a new example from some kind of a random process. So kind of bypassing the whole normal or standard motivations for entropy, I would say spectrum could be also interpreted as a measure of randomness. And this is kind of a pretty powerful statement that will kind of bring us to thinking about everything in a random way. But if your sounds are considered some kind of a random process that goes through a filter, you can start quantifying how predictable these sounds are in terms of tools of probability, and entropy is one of them. So it can be shown. I'm not proving it here. It's actually something that I will keep for later discussion, because there's kind of a powerful and interesting notion of entropy versus entropy rate. What is entropy and what is entropy rate? So entropy of a variable is basically some measure of how uncertain or how much randomness there is in a single event, in a single data point. And every time you make an experiment, you get a new data point, and you can measure the uncertainty about your next outcome. In some processes, in this case, this is for a Gaussian random variable, you can calculate these expressions. And if you want to relate this to spectrum, because you think about how different random variables now line up in time, and you go through the FFT and you do the spectrum, you can show that every individual sample in your random process is actually, it's factored by the variance of that sample, and that variance could be calculated as an energy of your spectrum. So the integral is basically you sum up over all the spectrums. Here we take the spectral amplitude. This is actually power spectrum, if you want to be precise. But if we take all the energies for all the frequencies, this will end up with being the variance of your signal. So the uncertainty about a single sample is kind of related to the overall energy of your FFT. So this is one. But now there is this notion of entropy rate, which is kind of a little tricky, but it's a very important notion in information theory. And also, if you think about machine learning a little bit in terms of information, this comes in very early, or as a basic concept. Entropy rate is actually something that reduces your uncertainty about your sample if you consider a lot of samples, right? So if you code in a block, if you take a lot of samples and now you think, well, actually I want to consider the uncertainty of a long sequence of events, actually your uncertainty per event, so we divide this by n because we have n events, your uncertainty about a single event is much smaller. It can be reduced a lot. This is kind of what allows us to do block coding. Because if you think about outcomes of throwing, let's say, coin, flipping a coin, if it's biased coin, you can see that for long sequences of flips, if it's a biased coin, let's say it falls, 3/4 of the time on the head and 1/4 on the tail. If you look at the long sequence, you would actually expect to see 3/4 of heads and 1/4 of tails. So your uncertainty about a very long sequence becomes much smaller. And this is a basis of a lot of compression theory ideas that you encoded in long blocks. It can be also shown that, and this is in the next slide, that equivalently, you can think about uncertainty of your event, of your last event, or your one of the measurements, given all the previous measurements. This has to be proven, but this is why it's called the entropy rate. And if you want to relate this to spectrum, actually we see that this is the log of the spectrum. So the interesting thing is, if you remember, we've seen this becomes our average, right? That's our and this was something that if we put this in an exponent, that becomes the geometric mean, right? So arithmetic mean, geometric mean. So this is where we kind of can go and show that this information rate, or the spectral flatness with a log, is actually this difference. It's the uncertainty about your single event minus the uncertainty if you predict your last event, if you look at the block, or if you predict the last event from all the previous ones. So again, we are not proving this yet. In the previous slide, we said entropy rate is basically encoding a block of events and dividing this by the length of the block. You could show that this is the same as the uncertainty of your last event given the past. So in some sense, the slightly different interpretation of this in practical terms is that if you have a nice predictor, if you take your past and you're able to predict the future or the next sample, then the uncertainty about the sample is much smaller. So this is basically the entropy of your prediction error versus the entropy of your data. So the information rate is basically telling you this is how uncertain your data is if you don't consider anything about your neighbors, your past, the blocks, just a single event, versus what is the entropy or the uncertainty about your event if you do use contextual information. Basically, this is the entropy of the error. So somehow, and many times this is considered also the prediction gain, or related to the idea of how much information you gain from predicting something. So the interesting relation here, and this is kind of my motivation for a lot of the stuff that we're going to show later, is that the spectral flatness, or at least this kind of a transformation through a log, is very much related to the idea of how predictable a sound is. And if a sound is flat, in some sense, it's noise, it's not really predictable. And if the sound has a lot of structure, like spectral lines and periodic components, it becomes much more predictable. And this kind of suddenly kind of gives you a possibility. I'm not saying this is ultimately the correct interpretation, but just another way to think about structure versus noise is something which is predictable or not predictable, and kind of can take this idea one step further, and this will be my last slide, and think about music in general. So if you think about the idea that we want to distinguish between noise and structure, but maybe you can take this idea to the level of bars and measures and maybe complete musical segments and pieces. Can use maybe the same idea of structure versus noise and think about now measuring entropy over chunks of sound. Maybe you can take this also in the symbolic domain, and we kind of measure the difference between the uncertainty about a single note or a single measure versus how uncertain it is given all the past. So this is kind of the idea of information rate, where kind of the motivating slide here is that you assume that you have a listener who already heard the past. Now the past could be the past of this musical piece, could be the past is his whole musical education and training, right? He has expectations about music. So when a new music comes, he tries to reduce the uncertainty about that music by conditioning this on the past. So this notion of how surprising or how complex the music is versus how much a listener can explain it out. This is kind of explaining, this is the prediction error. So kind of this notion is called music information dynamics, and it was a term that came up about 10 years ago. No, it's already 15 years ago, I think, since we kind of started thinking about this idea. And there are quite a few people using this notion now about analysis of music. And it kind of gives you this sort of very abstract mathematical notion about what is musical surprise, what is musical anticipation. So kind of this idea that the listener anticipates the future of music by using past knowledge, music he heard so far or learned before. And such prediction reduces uncertainty about the future. And in some sense, this is kind of a mental process that goes in. And if we can measure this in the music, maybe we can correlate this to what's going on in music, in human perception of music. So this is kind of the idea of, I think we kind of ended the show here. Let me stop the recording and take some questions. We actually went over time a little bit, but I hope you could still, yeah, found it worthwhile. All right.